So, good afternoon, everyone. It's my pleasure to introduce to you this EPM speaker. This is Sonjoy Majumder from IIT Kharagpur. So, it's in 2002 from Indian Institute of Astrophysics. And actually, I know him since then because at that time I was an MSc student and I was visiting Ali as a summer intern. And I got to know his school actually I got interested about the PEC since then. I worked on PEC experiments and all these things. Okay, anyhow, coming to Professor Sanjay Majumdar, he, after completing his PhD in 2002, he went to Germany and did two postdocs on mines, Munich and Karlsruhe. And then he returned with the faculty position at IIT Madras. He stayed there until 2013, 2009, yeah, and then he joined to IIT Kharagpur. And since then, he's at IIT Kharagpur and now he's a full professor. His main expertise is quantum optics, quantum information processing, and regenerate gases like BEC and regenerate Fermi gas, and looking into many body physics in those kind of systems. So with this, I would request Professor Sanjay Majumdar to start his talk. Thank you. Thank you, Professor Sholette, for your kind invitation. So I would like to start. My name is Shanga and Blush. Manja, remember present or listen for front of you. Title is little or this community. And I think I will appreciate the time when make the topics appreciable to you. Okay. Like when the different terms and but this is one of the present technology which is has a very advanced future. Okay, some still quantum technology. Okay, you will see that applications relevant. So, before starting, let me introduce this first time I'm coming and I'm from very like this team. Okay. And that time I used to be the once in a while, but after that I never came to call today. So this is the first time. So let me uh, start by introducing my group. And, um, uh, something. Let me introduce our group. This has been present in this slide. So I introduce my different areas of the work. Mainly for systems, like data interactions, and there I actually also extended my work on something which is called post-nested condensate, of which I will talk. And there are different kind of phases comes out one from I will giving on one end separate the explain on that is one first of the problem is on the structure for the these process we call this. So the line bearer infection parts also will work extensively on the quantum stability and diagnosis. Other side that is purely actually demanding from the students. Okay. Though I'm not that expert, that is quantum computing and quantum information. So that is the recent one which we have been working on and got very good publication recently. Also get got into the quantum machine learning. They are actually some of the strength allegations. Okay, we also do that. So let me also introduce for the ex members who actually enrich our group over the years. So they are based different administrators. Okay, so these are the foreigners ex members and today's presentations and keep on the work based on the thesis of the formula. And Subrata is ex-member who is here again. Shomode, who actually sends on his thesis, also collaborating in this. So, before going to that topic, as I do not expect that you know the research and condensate part. I shall not right. Okay. So if I just bore you in the introductions, please stop me because many of the things maybe it's redundant or it is very elementary. Just stop me. Okay. But I prepare in the sense that it may be useful for or it may be uh, good for some. So please bear me in the introduction. As you know that there are different phases of matter. Okay. Like you can have the most general solid, liquid, and gases. Among them, liquid and gases are quite close. Okay. So there are two extremes in this form phases and information. One and another, one and another. Our temperature is actually indicate the plasma. So another same problem. And in the left side, if you can go beyond the critical temperature, you bring down your state. So you'll be achieving a system matter which we call reverse sequence. These also is known as superfluid. And let me introduce what is superfluid. So, so that is the first thing which I have to raise that uh, discuss that what are the properties of solid which is actually convention compared to this thing. As you know that due to the laws, okay, the three limits we have, we can discuss the viscosity is involved. Okay. You see all the features actually are viscosity, like a driving force. If you just have a flow, you have a driving. So all the whole sort of fluid will not be moving in the same velocity. But where if you have this superfluid, you have that you will see that all the parts will be same velocities. Okay. So that's actually it is signature of this. And one of the famous example as no but yes, like is AR4, which is one of the greatest examples of that. There are very distinct features of the superfluid. Like as one so the seal all the threads are going in the same thing, but this can't have a friction. So the friction, so yeah, right? So we will not expect that there will be any dissipation in the room. Another thing that if you find any means makes the fluid pain to be lifelong. It's actually as a lifetime is infinite. So by like if you can just rotate by the light, because you have done some light metal detections, you know what? Well, actually show that use the light which is experimented also. Use the light you can rotate the fluid and you get vortexes. Right? You can get some kind of vortex. This is the kind of vortex can be generated. Unlike the classical plate, where actually rotation of the liquid overtime in the bucket will die down. But here also creating that's an important. But once you have superfluid, if you can bring down the because this is a quantum, so you go to the right honestly. So the ground state of the system or the superfluid is known as a sample length, minimum image. Small sense of progress. Where actually all the atoms are not most of the atoms of the atom energy. So that's all actually this is the lowest energy level. This is step which you can understand. But I think all of you know this one, how to, I don't know, those to know, the few people that most of this. So, then we use laser light and using the comparative technology, which is known as Doppler cooling. If you can shine the laser, which has a that light transmit from laser to the metal, you can do the zoom on things like gas play and shine the light from the opposite directions. So that you know that if you take a reading of gases atoms in the gas actually can be moving with the kind of energy now motion can be restricted from results. Right? Small momentum from the light. So if you are having some activities, trying to write from functions to some of those gas restricted in some positions. Similar technologies. But one other way, people could achieve the temperature, which is some hundreds of microkelvin. But it has been, I think you have gone through in your undergraduate course, statistics, to consistent condensate, one need to do some hundreds of nanometer temperature. So from microkelvin to the nanometer, these straight jumps on the station of the ocean. And people have worked a lot on this, and interfaces are not over time is given. Those five items that are nice. But the truth was they invented a lot of things which are very in that. So at the end of it, at 1995, okay, two groups they have put bracket to put achieve the whole system condensate using some simple technique which is called log. This is not a theoretically or intuitive reason or any um, tough thing, but it is like if you consider that inside a crop which you have and outside, we have it's poor. That technology is you understand that on the surface of the molecules interact. So they are in excited state because they are not to go out. So that loops one is not out. So and if you are considering or the container which you have now, so you will have more and more molecules from. So you can think about this kind of a where you can use the harmonic equation and bring down the potential height or so what will happen that we will expect that more of the atoms which are excited every spin out. And what is the but then we have lower kinetic energy or lower velocity of the atoms. So like this they will have their atoms. But not in those things when you are not the pressure, you can measure into the potential. Find out that stop the atoms. Calm down. And in systems. That is the basic technology which you recognize. Now, as you see this picture, which is very popular, I think you have most have seen, this is in a local space. Now we said that if you can bring down the temperature, which means that the tension has gone down, what would happen that in the which as you the spin of the atom, okay, in the momentum, which is still on zero, okay, around this zero value. Now, as we the temperature, you see that in the zero value, the most of the time is not now. That is the stage where the spin is achieved. Now, it's quite in that once we come back in the atoms, or most of the atoms in ground state, it will be like all the atoms are in similar state. So you will get coherence in the system. It will be like a laser. Like, so this is what atom laser. And the way laser is used nowadays, we expect within few years the BC also can be. Advantage or disadvantage both are. Advantage in the sense that now signals which are used in the laser come has mass. Then advantage. So what we expect most of the atoms are now okay. So that is all. Now, I'm using 5 euros, not money. So we are about to understand. We want to understand the physics of the systems for such a condensate. One simulate it. Sure. So that what are things are available? Now we have some motions. And you have a trap potential. You have a trap potential. Okay. So that is trap potential, which is looks like that you can really with harmonic senses. You have the figures of the association. That's like a wide range of generations. This mechanism. And on top of that, you will have the expressions, which you can consider like that kind of contact infection or now friend most of others minus 1 others. And the amount of or state of that interaction is can be understood by selecting I know. Yes. So the G factor which is actually coming, and as you understand, this is a straight and a straight. Okay. So what would happen that what you will get the understanding the mathematical impression based on the studying which you can get it from experiment. So these values you can get from experiment and for the play with. So once you get these things, next thing is that you experiment. This is one simple simulation which I will show. So suppose I take that one of the very brightest candidate that is and what I can use it that all the items are one of the hyperfamiliar. I think you understand what is written here. This is the quantum area, which I think by the interaction of the nuclear speed the and the momentum of the electron. So that interaction gives that you are having a 100 can use on the media and allow all the atom to turn down to the and what we have taken, if you can notice clearly that it is symmetric in xy direction and omega is like omega, which is 50 much. This is we are taking from the experiment. Yes. And if we can confine the motion of the atom in z direction, that can be understood like some of the oscillation. For example, frequency is very high. So if you oscillate something very fast, then you might be able to recreate the motion of the particle in that direction. Isn't it? You not see that because you see that it is in the new position. And this motion is that, and like this. Then you see the motion is not there, but it is in new position. So what is the fan? Results say, and also the fan as well. But if you rotate it slowly, you see all the so it's like that. If you say no more, you see that the atoms are it has been atoms are position. So similarly, if we can have an same operation of data action, we have our spotlights of this minutes. So let's expect that. Let's expect that all the items will be expecting. It's like a big ship. So and what I see this color. So if you see the color bar, it shows that the yellow is the most popular and then that is most so that means you will have the center host population and you will have the population area around research. And experimental research will also observe. And you see that there is sort of life. So we have about the minus say, this image or indices. And you could also see like this feature. So you also can see some other examples. Like one more thing is that as we can see that the distribution of the number of atoms or what I'm saying that composition is in the oscillating quotient. And the central region is the height and I'm going for the to go down almost to 0. Similarly, the experiments, okay, which show that similar kind of structures like ours, and those are done in the recent. So it shows that if you can take this way of calculating as the kind of a Hamiltonian two way, okay, like this Hamiltonian, and solve the Schrodinger equation using Hamiltonian function. which means that some kind of average effect of the impressions. So can consider also known as the very like having. So you have to have this function what you get that is what cross relations. So that is actually very approximate atom and actually having relation of what other names. So using Grosvenor equation, what you see, you could see the future, which is which is actually well established and can make or can establish the experimental results. So now we can use the Grosvenor equation and do the calculations. And today's talks, we go a little more. What we talked about? We talked about the atoms. That again, I try to bring down all the atoms to aim at the hyperprise. And you can choose some atom, like which has multiple atoms, which is almost bigger in energy. Like example, which here is the sodium atom. The particular isotope, what would happen that one combined units that is it is actually correct when class check. I use the industry chase and one. And then the subnet case that is any like say angular momentum can have the alpha g of now those applied this sentence of different means that these are same energies. Now what you can have, you can choose this kind of candidate and try to pull out. What would happen? You will be able to understand and know where atoms will be distributed in all these levels. So here is the example experimental picture is given that you have n equal plus 1, n equal 0, n equal plus 1. So what you see that these levels are though they are not same population of the they can be linked together. So it is as if that since we are talking about atom is okay, is as a whole a gigantic unit which has angular momentum x, the speed is one, and then it has a sublevels spin component sign 0. So remember the states of those atoms okay, can be understood as if that you have a spin system is there that is 1, 0 and minus 1. So we can say that this kind of candidates can be used for spin one process policy. For their spinor. So here in 1998, this is the same from same Institute of Ornithology. They could show that using some technique, okay, so that means plus one zero plus one. Yeah, I will explain that this log of B. Okay. And if you can shine the light, one which I call the little push, which is actually in far detail, or it is not close to the desired frequency, what we able to grab all the three levels of. So what we saw that all the 300 items actually are available in this. And what happened when you find for the single questions using the other real one which are discussing. We actually broke the translation symmetry. That is one. But here, by condensing that thing defines a component of spin and using spin language. So what you do is that you also program is spin. So this is actually mathematical law. You see that if you can say, or if you can bring down the atom, that is actually breaking the symmetry of SO3 cross P1. So this is a little interesting in mathematics, so they can understand it. So we can understand that there's an MIT group in the same year, 1990, they also put reports on actually work on the visible from catalyst group. Okay? Uh, spinor music using sodium. So these now uses sodium in 1995 also they are sodium kind of. But particular to anything isotope sodium, they could show that we have a three spinors, hydrophilics, and using the magnetic field, what they could show that the condensate one from this, they could even all of the seven. If you use this, their energy levels of speaking, and they have shown that the term of flight, okay, they have answered which can, or if you when the incident starts spreading, you see the whole the other area. But because of the magnetic field, they want to hold in that and 3 for 1 second, you see the interval now environment space for the item. See, I use. So that is observing what people the same time of flight. So, okay, I have introduced you on find out whose physics one is that is spinor. Easy. Okay. Next question, okay, you made it fine. Like I need the laser. What do we use of this? I can make the laser, but unless I can apply something, there's no way I can get the laser. So I need to apply something. I need to interact laser with something. So like I need a matter. I need someone that laser to interact. Then only I will be seeing the other point. It is a point laser and it is the function. The width. So once I make that as parameters, I'm saying that will be easy. So I need to have some kind of interaction. Like light, I'm interacting with the matter. Here I have that. So I need to interact the light to understand the characters that matter. So I can have light or I can have any other field, like magnetic field. Characters. So I need to actually shed light on the integrated connection between the quantum gates, which we use to talk about scenarios, and as if that's in the spinor systems, they'll be behaving like a condensate. So by interacting with the field, I will be able to show that they need some of that condensate which the interest walking with the teachers. So I will now let's see that how it can be done. So in terms of applications, what one can show that spinal is okay. It is really technical. Can be having the uh, magnetic ordering. It can have that some of that things like topological excitation, like the upper functions. And this is it at the down level also. It can have topological excitation. It is energy levels and some there. At the down level, but topologically it is state. So that is the topological excitations. Similarly, we can have the events. We can also see different phases, quantum phase transitions. Like phase transition means that as you know that I can look for that flight to get it to yes. These are different phases. Similarly, you could get certain conditions. So that phase transition. Like here, what we can do is we can since we are having spin systems. And some means if we make all the atoms are aligned in fractal relations. It will be like a thermodynamic system. If you have a opposite direction, then atoms, spin, okay, you can get by some means you can make the atoms spins are opposite direction. You can make it. Similarly, you can get some kind of topological excitations like line or point defects, Skyrmions, which I have defined it. So this is a focus of today's talk. Okay. That this is one of the phases which we can get and we see the bodies of issues. Okay. Also, what you see that these spinor process are a very good candidate, especially the Skyrmions, okay, for the qubits, quantum qubits. So that can be used for the quantum entanglement when it interact with light, or it can be used for the quantum field. So there are multiple applications of systems which can be installed. But in terms of the simulations, if you are exploring, so what are the changes we are doing? What I told you that earlier that we have kinetic terms, we have the track potential, we have the atomic interactions, which I have talked about that point interactions. But instead of that, the atomic interactions, now what happened, not only atom has interacting with other atom, like a scattering theory, but also they have spin now. So that spin plays another important role. So what you can see that so we will have atom interaction like Schneider square. Similarly, you will have something, some other terms coming up due to that consideration that the function has a spin itself. So you will have a spin density function comes. So what we'll have two terms coming out. What? And in these two terms can be understood as an automatic interactions where you take a few atoms together and suspend that interaction. Scan. Now if you have two spin systems, okay. So what are the total spin you can have? So you can have there's a possibility that you can have that since it has spin one system, spin can be two part one and then zero from the angular momentum. Right? Now what happened that one will be some constant and so that have spin possible by zero right. When that zero will be there, that you will have the most possible scenario will be that you have something or anything in the matter of point. And when both of them are both of them is out, the spin. So you have circle not which are corresponding to like zero. If you just compare state, so if your A2 is large, it is lower than A0. It is lower than A0 means that A2 is more permanent compared to A0 in terms of energy level. So that you will have when one is set, will come to the speed where all the speeds are different directions. Doesn't it? It means that when all the speeds are same directions. And if you say that, uh, A2 is lower than A naught, that means A2 is created from the spin configuration while its spin direction is same directions. I mean that is preferable in terms of energy. but ultimately A2 will give you the energy. Okay. So if you get a condensate, it's in that right, we get permanent. But in opposite one, no action. And infinite will work. So what happens? We will get extra term in the system in the Hamiltonian. To understand that it will accommodate the spin degrees of the. And that means you are modifying your the whole hospital situation for all the happiness, all the happens of the atoms, spin components of the atoms. So you are modifying the hospital situation. And you start. As an example, let's take that rubidium again. Okay? This is magnetic in the sense that I choose that A0 is greater than A. It means star. Okay, so it's star. And that gives me that C0 and C2, that coefficient, that is this one. And if I choose that omega x is 20 hertz, and omega y is 6, and omega x is 20 times larger than omega x. That means again we are doing dimension sections honestly. We need to show that to give a distribution of the atoms in three different planes of the spin 1, spin 0, spin minus 1. So here, spin 1 and minus 1, we have the almost similar kind of still sign. Spin 2, sorry, spin 0 will have more restriction or more density. The question is why is that biasness to the spin 0? Why that spin 0 is more preferable? That's because if you see the interaction terms that the spin density terms, okay, if you just look at it, the way if you just see it in the different of the side 0, side plus 1, side minus 1, what you see that because okay, there is no direct way of conversion from the side plus to side minus, only it can be add to the side 0. So this is the 1, 2, this is 2, 1. So that is between the side plus 1 and side plus 1, 0, side plus 1. So through that, okay, uh, uh, conversion, because the side plus goes to side 0 or side 0 to side 0. Now, plus and side plus, they cannot convert it. So they have to go first side 0. That's why in that side is more compact. Density size, net density. No, it is for a particular direction. See that collision from here it comes here. Operating from the end. Here it goes back. Right. So this is not considering like a steady state. There is no sizing of density. It's there, but I think maximum not for a direct term. This is for a term. So that's and density from coming from this term. Okay, so you start with this level, minus and sine plus x. No, then there you know. So it is actually very big, but I have to if you start with the, all of them are same formation, okay, then what would happen because of this term, you have a conversion from the side plus to side zero and China. So you have two channels coming to the side zero. Whereas there is no channel from side plus to side plus. Okay. So if there is equivalent channel side plus to side plus, we expect that these three distributions sit there. But for a particular time, if you see that because more channel available for hiding, we have no population. So that's it. They do. So I expect that this will be the transfer configuration. Having said that, Once I prepare the systems, prepare the condensate, I would like to see what are the uses of it. Here comes the guide. What engineering is the title of presentation. So I said that engineering, Stania's engineering. So that I want to prepare the system using the external field. Like, for example, 2 years back we have done, we could have the being both as a condensate and create some books, this is a kind of point boxes, use some kind of light. So light is like a parallel in systems. We just want so we can see. And then what we have to think about what? Now, some kind of a thought so you will get some kind of a condition. But here, because you have a superfluid, what will happen? The whole system is working. That is why due to the cycle example, you can have variables. And you will get instability or autonomous system. So you could train the this. And robotics have a lot of applications in also training process runners. So this is one of the applications which you can do here. Okay. This is so like that. What we would like to have, would like to have install the current we like to have, which is used by electric field. We are using magnet. We have external magnetic field, which you have to use it for engineer terms. And if we can have the on this, prediction of the like deviation in the market, yes, you are about to do that implement magnetic field. So that term will be like P dot S. And what we see similarly in that this say plus 7 us, you will not have any direct terms. And what would happen is when that magnetic impact is you will have that interaction between the you have psi plus to psi here or psi minus to. Okay. So that is the way. So if you have into a magnetic field, okay, it will affect the side you. Okay. So that magnetic field side is affected by magnetic field of it on side plus action. So the through the thing. Here is a example. So let's first have that the magnetic plane, but yes, having the proportional that means it has a linear okay, with some value of which is taken 0.5. Okay. And if you can consider visualize G2, if you give that a spiral receive, you consider that what you see that at x equal to 0, that line, along this line, there, you see that there's an oil or depletion of the atoms or n equal to 0. But that depletion is actually compensating by the amount of atoms, okay, in the plus and minus feature. So you will have denser this one density in the plus and minus one, but that will change. So what we expect because of this extra magnetic field along the gradient in x direction, you see that modulation of the density in the x along x all things. So you will see that fragmentation is coming in the engine. And what would happen if you look at that moment of space distribution? You see that as I expect that when they are condensate, all the atoms will have one zero momentum. So at center, I expect the density will be high. And around the center, there will be density, right? Just G. But what happened due to this kind of external thing? Okay, you see that the non-zero values of the momentums are the ground state. This is only a ground state. So there is a modulation of the densities. So density modulation is coming. And if you just see that none is a actually you are getting the answer. So then using that, okay, you can see that one order of lambda that is formation. And interesting thing that we don't explain that very that's because we don't have any single point. Similarly, if you can consider the magnetic field gradient along y dash, you'll see that one axis is same picture. But here that fragmentation will be for the n equal to 1 and minus 1. That's because the way that there. And n equal to 0, you get all the configurations. Similarly, you will see the density modulation in the motor space in the animations. So that is just purely well applied magnetic field, which is a gradient linear gradient. Now, since we are having the system which has speed, I have privilege that I can get that external spin orbit. As you know that, how we have that internal spin orbit motion of the electron or nucleus. Here, we start where we get from electron spin. So that is spin. But here, what we are talking of external spin orbit. Using the external spin. So, if you can just see this picture, here what I mean, you can think about this is a spin particle which has a spin. Now this particle is oscillating like a cloud. So once it state, what will happen? You can have some kind of control bias systems which actually give the electric field along the direction of particle direction. Because of the motion of the spin particle, what will happen? Spin, we make that spin and motion of the particle stop. And what we have, we get the scalarity. This is a technique which is very popular and it is unlike the classical scalarity which many experienced people use. And where actually you can have the internal products, okay, the similar instance. Then you can have dynamic change as the this is the part of it. So, and we see that this is similar like motion of the electron carried due to the spin on coupling in the solid state fields. So similar things can. Now, if you have a spin on coupling, this is like a one thing I just forgot to say. When you have a spin on coupling, wire voltage is much. Then only we will be able to appreciate the kind of spin thing. So what will happen? You actually need to go in terms of raising your particle, leading stimulation. So this is the realistic scenario today. And if you think about that, your systems of where only signal in the condition, what would happen that this realistic square company will invest magnetic structure. So, which is known as, I don't know the way to pronounce it, but uh, DL. So that what will happen? And you see that last picture, the spin directions, okay, changes Now, what will happen is the direction will change, okay? And you will have an interest Hamiltonian, which will be dependent upon the spin direction, which are now modified into spinor. Now, really it will be like it will be looking like a hijab, like a topology. Like the animal will hijab, which is a close around this. Right. So all the arrows will over directions. All the spin direction. So we have like a spin wind around the unit sphere due to the induces. Now, if you just put this one, okay, in the two dimensional space, what will happen that uh, you will see this kind of spin directions. Where the spins are perpendicular, it is shown, they are aligned this way. Or this kind of, depending upon where, how you are doing. Now, if you measure the intensity of these spin directions, the way it is changing. So these are the velocity 0 and this is velocity 1. So these are distinct characters of the spinor systems. Okay. And these distinct characters are known as scalars. They are called scalars. So what is that? You get that defined quantum value, 0, pi, or some other values according to the spin orientations. So you can get, as I was talking about, you can get like a unit system, 0 and 1, changing the helices. So that's why Skyrmions can be good candidate for the quantum field. And as you saw, these are topological excitations, which has a normalized effect. And this actually you can't change by itself. That means that once you prepare this state, you will be having their finite knowledge. And you need those kind of systems for the quantum bits. Because once you prepare, you want them to stay in the stick in the state for meantime, so that you can use the quantum. So what we did is actually we got standards. The name of standards is actually proposed by Tony's Standard. Actually, he didn't want that answer. What he wanted to explain how the proton and electron are confined inside the nucleus. So that was not known. So he wanted to have some kind of topological structure, topological charge in our sense, which can be altered by any other field or actually invariant. And with that way, he actually wanted quantum going on with downtown change or spreadsheets. So that actually you wanted to define, and then you are using to explain that how nucleus, proton and neutrons are singularities. But by the time, at the same time, strong interaction was people could explain the systems and nucleus. They are confined to the same interactions which is possible to. So that time, things were not in the organized. But later on, that Allah and then people saw that this can be a structure for schema systems. Okay. For any kind of a management theory. Okay. For scheme is not really important. And what you see that in this is other part of the pictures, so the projected picture of the actually you see the real space this time, which I showed that basically touch the instrument. So each arrows are actually giving the direction of a scheme. I just have to rush up. Mm. So what happens that one can synthetically, okay, or generate this spin-orbit coupling. Okay. The using stuff using two different conditions. Okay. People can discuss like this and spin-orbit coupling. Similarly, second was happened there. Okay. Um, you was okay, so you know that. So, because actually we have this in many presentations, what I use this as an expression where we understood that the orbital motions are in fact spin motions. This P and is orbital motion or linear motion or motion of the body. While this is spinning these optical or vertices spin on. They are actually interact between the communication. Here gamma is telling you the spin and the will then identical triangle spherical. So if eta equal to 1, which is isn't interest, what we'll get? We'll get cos of that. There are a lot of proposals and then don't know that any way alpha spherical and Skyrmion is one. So, yeah. But we can't touch it. So what you can see that putting down as 0.5 and as 1, okay, what will get is the distribution of the spin atoms of different compounds. Here you see that there are vortex generated. Okay, so this is like a anisotropic task. So that gives the vortex is like the component Q and minus 1 for positive and alpha. For eta equal to plus 1, sorry, plus is movement, not about bonus. So what happened in the atoms from center region, that one have component this. Overall, we see that there is no hole like in vortex. Okay. So put them together. So this is called holeless vortex. But from the phase diagrams, you can see that so that will just now what would happen that now we need to know that if you apply this magnetic field or if you apply the spin orbit field as a submarine, what would happen to the spin structure of so if the one which I showed that density plot, you see that is the spin directions. The way you can calculate density by spin decimal using this one. And what you see that the all the spin, if you zoom out here, all actually converging way down the station. So this will tell that it will see like that the scenario which we got equal like 5 types of the next. So that this is a scenario switching. In the halo region, what would happen? When we see some information, you will see that this is another topological signature that's happening. What is more important now, you can calculate the topological charge and that actually using this expression calculate. That will actually give that whether there is a real phase similarity is present or there is a filament spot. So that actually you can find out that number. And if you integrate that value over all the space square, okay, what you get? You supposed to get a 1. So that is the topological charge, topological charge density. And this is concept quantity. All this. So that is from the Genesis. So this is the work which is recently published. What is the aim of to investigate the to undergo the competition between that spinor and topic, which is still manufacturing and the ground state to harness. So by playing interplay between the spinor and topic, the external. So as I showed that using the linear gradient, what you show that in presence of the spinor and coupling, what you will see that you see that there's a space generated in the all the components. And if you see that this is the specific, okay, plus one and minus one is the value of the vertical of different color. So these are positive constraints. You will see that two bodies are generated for any particular those one single horizontal vector. If you see that the space structure, that the standards charge density. So there, what you will see that this is plus one and this is minus one two plus one. You see that already charge density. And if you see that, so that is the spin structure is this one, or the spin directions of the which is doing one. So in this region, you see that all spin are directed towards. So they are actually you could confirm that. So here, what would happen in this case is you got metal charge. It's positive. And interesting point that what is now, if you increase the value of the gamma, which is state of the spin at point, you would recognize this for the stones. So by putting the value to different again, whether y or x direction, now change now like this. So that is interesting external point. Similarly, if you can have the sinusoid or the periodic gradient, the gradient of the magnetic field, okay, you will see it's interesting pictures. Okay. You'll see that you'll get what is spawn. You see that also you see that blue colors of antibodies. So you see that different composition. And similarly, see that in the speaker structure, you see that terminals and case comments which are intestinal and blue light. Blue color. Okay. So they are actually can observe in terms of the speech. Now here is a dynamics what we want to see that in these cases, okay, if you just see that how the stallions are changing or how the skin structures, what you see that stallions, this is the stallion which is the center, and the stallions are the same. You see that there is a discussion going on. So in that stallion. So you saw that there is center stallions and the stallions are external. And then from the initial point, you see that oscillation is going. Some are actually going, some are start going out, and some stars are going out. So for the video. So, so with respect to the equilibrium equation, we see these oscillations, okay, and which can be actually analyzed. In this paper, there are different examples of which I am not going to call it back, and very interesting. And in subsequent paper, actually, we see the dynamics, which is not yet submit. Okay. So, instrument problems. Okay. So, we see the different angles. So, what actually, just for one more thing, I'll just plus. We could say that there is periodic persistent identity in both X and direction and get the certain points. Now, once you get the certain points, you get forces. Okay. So, along with the scalars, you can see that what this is. Okay. This is this. So you can play with the different techniques which are theirs. So I just would like to conclude that what we have discussed that common agent of external including section of magnetic or very magnetic field, and what it show that what is the effect of it, the spinorities or spin ones. Especially our interested was that how the entropy of the dissociation is strong load, or how the periodic structure of magnetic field gives a certain point which can in systems. So spin orbit coupling breaks the symmetry of systems and is responsible for the induced unstable systems. Magnetic field what we should observe was uncertain certain point structure and incidence of what the horizontal system. Similarly, what we also observe that certain skin textures are observed as a consequence of interplay between the periphery and the spinor. So we saw that Buddhism and Islam together and how they know in the system. This can be actually experimental and verified as more experimental, which will maybe coming up next. I think I'd like to thank you for the kind questions. Thank you for sitting on my questions. Yeah. Why the topological form of these experiments cannot be altered? And particular. So what is special about and when we use the magnetic field can it be gone? No, no. So topological charge, which it will within an environment, yes, that is remain from the mathematics because of the calculation which I showed. The transformation that shown that is automatically that you can see it in the real life in the simulations. What is special about that technology? But that's because of the symmetry. If you have a symmetry, something will be possible, isn't it? In systems. If you have a symmetry from the Markov theorems, all that, and same property will be possible. But the kind of transformation, the things which it means that but externally, if someone wants to alter, it can be. Depends on. So that whether it is pumping extra environmental systems or extra. So here, if you see that whatever it was the initial, even if we apply the extra uh, spinner cup, systems. Okay. So that's it. There is energy. Yes, the energy. Especially only energy system. What are we doing today? All spin much. Recently, there was a nature paper where they had talked about the discovery of new state. A new state. New state, yeah. It was, I think, Bose, chiral Bose liquid state. Like, see, I don't know about the which paper you are referring, but it's kind of what in the condenser systems are just few ones. So since the Skyrmion, as I said, that the total mechanical charge is very, and this can be actually experimentally observed in the process condition for spinor cases. So these are the mean scales of the process condition. So in that sense, this is the state. I think mostly the was glass. Glass also glass. What's nature paper? I don't know. I don't remember the. What are the glass? Egg systems. But glass is in the system is very. So that is again like another phase of stuff. Yeah. Really new state of matter. Yes. There is compared as a that is a state. So the current line. Any other questions? I have one question. So in these all these simulations, do you consider any temperature of this operates zero? Unfortunately, no. As we are doing German temperature, hospital situation which actually tells you that you can consume temperature. And in real life, it's not zero. So if you take it into account how much any point that is very close. Usually, it has been observed. What is that? The fifth you will see. Okay, experimental. All this effect actually put was explained. Okay, this is the new thing. So that's why people are happy and still want. But there are people which actually going that on using that multi-configuration or this one time-dependent multi-configuration. Okay. You put it like it's called pattern pattern. So the horticulture kind of system, time-dependent method. If it not all the time. Stochastic. This is a stochastic approach. There is a stochastic way of calculating. So then you can take that Actually, we were far from condensate. The temperature. And another question that you have looked into sinusoidal dynamics, also looking into the phase band resonance, will give you some phase of the starting of because this figure is the video has lot of phase band resonances. We can discuss this one. So yes, actually, we are one of the people actually we could show them the system that they are prepared to check. So I think the impression. We have to find it. Okay. No, actually, we show that if you take that beautiful granite scanning, and you see some of the mystic, but Skyrmion people haven't done it. So maybe it's one of the things which we can do. And okay, if there are no further questions, let us side question once.